So this is just going to be a code walkthrough. This is going to be a code walkthrough of BlueStore. Obviously not going to be able to get through all of it because it's pretty big, but I'll get through some of the basics. So BlueStore is an object store backend for the OSD, which means that it implements the object store interface right here, object store class. This is the generic local storage interface that the OSD uses to store all of its data on the local disk. BlueStore is sort of the newest implementation, and it's the most least encumbered by legacy design decisions of all of them. But object store basically has two categories of operations. There's a whole bunch of read operations that are synchronous and blocking. So if you do like a stat or a get at or read, it will block and then do that operation. And then on the right side, everything is done in terms of transactions. So there's, in this object store class, there's a transaction class here that captures a collection of operations that will all be applied atomically, committed atomically. And so it has things like, there we go. It's got like write to an object at an offset with some data, touch, set adder, truncate, blah, 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 all that stuff. All of that gets captured into one class. It's encoded. You pass it to the object store backend, BlueStore in this case, and it'll do it all atomically. So I'll start, I guess, with BlueFS, which is sort of one of the wonkier bits of BlueStore. So BlueStore consumes raw block devices directly, and then it uses RocksDB for all the metadata. And that's tricky because RocksDB normally wants to read and write files. And we're sharing a raw block device with all the data that BlueStore is actually storing. And so we somehow need to make RocksDB and all the data that you're storing consume the same block device. So if you look in here in BlueStore.h, you'll notice that there is a key value DB pointer here somewhere. I passed it. There, key value DB. So key value DB is the Ceph abstraction for a key value database, whether it's LevelDB, RocksDB. We have an in-memory memDB. There's probably some other ones in there. I think there's like a old Kinetic implementation. That's the database that BlueStore is going to use. So it's still sitting behind a generic interface. And in fact, you can run BlueStore with LevelDB or something else, but it's just going to put all those files in a directory in the var libosd db directory, which isn't actually very useful. It's good for testing, but it isn't useful for a production environment. In order to actually consume a raw disk and have the whole disk be consumed by BlueStore, then we have to use RocksDB, and then there's a custom RocksDB backend that we wrote that allows it to share that block device. So RocksDB has an abstraction called env, which wraps all the POSIX calls like file open, read, write, and so on. And so there's an implementation of that backend in the directory here called bluerocksenv.h that implements the RocksDB env wrapper. And luckily, RocksDB has sort of like a constrained subset of file operations that it does. So it's things like delete, create directory, open a file for reading, open a file for writing, and like flush, and like that's just about it. There's no rename. It's like the directory structure is one level deep, so it's pretty easy to write a pretty simple file system that satisfies RocksDB's requirements and have that work. So that is called BlueFS, is the implementation that we did. Which is in bluefs.h. So BlueFS is written as a standalone class that implements a simple file system-like thing. The BlueRocksEnv is the glue layer that implements RocksDB's env interface and passes everything straight through to BlueFS. I won't go into too much depth here in BlueFS, but the basic idea is that it has files that exist in like a very simple directory structure, 1 or 2 levels deep. You can, let's see, I guess you can rename, but I don't know if it actually does ever happen. You can open for write, you can open for read, and you get back a file writer or a file reader in both those cases. File writer is pretty simple. It's just got append, basically. That's all you can do. And then eventually you close it. There's a flush method down here that will flush all the dirty data that's accumulated on a file writer, and it'll flush it through to the back end. And the way that BlueFS is implemented is it has some number of block devices that it's allowed to write to. Right here. Block device, these BDEVs, which is our internal abstraction for a raw block device, which is probably where I should have started before talking about BlueFS. So let's jump there really quick. So block device is a low-level abstraction that is basically just wrapping a block device. It's an abstract class. So there are a couple different implementations. It provides a few basic things like read. That's assumed to be block aligned offsets. Read random is can be non-block aligned, and it reads directly into a buffer instead of into a buffer list, or yeah, to a pointer instead of a buffer list. There's a write method, which is blocking. So read and write, these are blocking variants, and then the AIO read and AIO write are non-blocking variants. And you'll notice all the non-blocking variants are done in terms of an IO context, which is sort of our equivalent of, I forget actually what the kernel equivalent is called, but it's basically a descriptor for the IOs that are in flight asynchronously. And then there's a flush, which basically will make sure that every write that's completed previously is flushed all the way through to the hardware, and the hardware is promised that it's actually committed on disk. There's some discard stuff that is only sort of half implemented, so I wouldn't worry about it too much. There's some stuff for managing buffered reads and writes, but we actually don't use that anymore, and this is probably going to go away in the future, so you can mostly ignore it. But the main thing is that, for the most part, everything uses AIO read and AIO write. These blocking variants aren't actually used anymore, or shouldn't, or used rarely. An IO context is the structure again that describes a bunch of IOs that are in flight. So there's some internal locking that's mostly used for debugging purposes. The main bit is that there are pending AIOs and running AIOs. And so in the BlueStore code, we'll basically say, I want to do this write and this write and this write and this write, and those all just get sort of accumulated on this list, on the pending list. And then finally, once we've described all the IO that we're going to do, there's a submit call where you say, okay, go do all that IO. And then it's actually passed to the kernel, and then the kernel does all the IO. And then we have a couple methods here to tell whether they're done. So you can call AIO wait, that will block until it's done waiting. Or what actually normally happens is there's a callback. There's a completion thread basically that's watching all the IOs that finish, and it will find out. It'll basically say, oh, all the IOs are done for this IO context, and it'll call a callback associated with that AIO, which is not actually described via this priv thing, but I'll get there for in a second. But basically, so you describe all the IOs, they're pending, and then once you submit them, then they're on the running list, and then eventually they're all done. And the way that you accumulate these pending IOs is by calling AIO write. So when you call AIO write, it doesn't actually do anything except add it to the IO context. And then once you finally submit it, then they'll get done. So we can look at an example of how that actually happens in BlueStore. Let's look at the write method here. Let's see, it's in do write. We're not going to go through this whole thing because it's complicated, but as an example, once we finish preparing our write ctx, oops, finish, it will eventually call. Oh, I chose the most complicated one. Let's do reads, because you can also do asynchronous reads. That's a little bit less complicated. But we'll figure out all of the buffers that we're going to read here, and then eventually we'll call block device AIO submit with the IO context. And that's the point where it'll actually give it to the kernel or whatever the block device implementation is. And in this case, we block because reads in the object store interface are blocking. And so once they're submitted to the back end, there might be 5 reads because we're reading multiple fragments of a file or something. They'll all get submitted in parallel. AI will wait for them all to finish. Then we'll grab the return value, and then this code will continue and with the other stuff that we have to do with the reads. So that's the block device interface. There are 2 implementations. The one that we normally use is called kernel device. So this implements the block device API, and it wraps the kernel lib AIO asynchronous IO interface that everybody uses if they want good performance out of the Linux kernel. So it's doing direct reads and writes, and it's doing them, they're O-direct, and they're bypassing the page cache. They're all page aligned, and they're asynchronous. And so, right, it's a simple block device. I don't know, the code isn't super exciting. I think the main interesting piece here, we open the device, make sure we have the right block size, all the good stuff. The main interesting bit here is there's a thread called, I think it's called AIO thread. Yeah, AIO thread. So this is the function. There's one thread basically that's watching for all the AIO completions. And so it's calling this kernel call that's get the next completed AIO. It's basically a buffer in memory that has all the completions in it, and so it's just pulling to get those. And then once it gets an IO completion, it looks it up based on a private field by casting the private to an IO context. It says, oh, this IO context is finished. And then it will, if there's an error, it'll log an error. There's a bunch of stuff in here for doing error injection. So in testing, we simulate IO errors and timing and changes and so on to try to shake out all the bugs. But at the end of the day, basically, if the IO context has this private variable assigned, then it's a callback, and it'll call a callback back into the BlueStore code to finish it. And if it doesn't have that, then it's assumed to be somebody that's just blocking and waiting for it to finish, like the read code that I just showed you, in which case it'll try to wake it up. But for the right path, everything goes through a callback. Right, so you have BlueStore, you have the block layer underneath that has this AIO interface that we just looked at. We're using RocksDB for all of our metadata. So BlueFS is sitting on top of these block devices. Most of BlueStore just has a single block device. All of the actual object data is stored on one device. Normally, it's just like a big hard disk or a big SSD, something like that. BlueFS is a little bit smarter than the rest of BlueStore in that it can use multiple devices, which is why we have a vector here, which is it's a fixed size of 3. So there's the slow device, which is the big one that it's sharing with BlueStore. There's the wall device, which is usually very small, and it's just for the RocksDB wall files. So it's like a journal, basically. And then the DB one is sort of an in-between device that if you have a bunch of flash that's bigger than the big device, but faster, then you can give that to RocksDB and all your metadata will end up on that device. In most cases, people just have two devices. And so you really just want to have a DB device and a slow device because the wall data is always going to go on the fastest device that's available. So if there is a wall device and there's room, it'll go there. If there is a DB device and there's room, it'll go there. Otherwise, everything ends up on slow. And so you just normally would have your big device, and then you'd have a big chunk of SSD, as big as you can make it. And as much of RocksDB as will fit will end up on that device. It's got I/O contacts to go with those. It's a little bit clever in that it doesn't have to consume the entire device. It'll consume parts of it. And that's for the slow device, at least, that's the case. Because it's sharing that block device with the rest of BlueStore. Basically, some extents on the overall device are being given to BlueFS to manage for its free space, and then the rest of it is managed by the rest of BlueStore inside of BlueStore puts all its metadata inside of RocksDB, and so there's a chicken and an egg thing that we have to avoid, which is why this sort of works quasi-independently. But yeah, so this tells us which extents on the slow device, or actually on all these devices, but in these cases, it's the entire device that BlueFS owns and can allocate for. BlueFS is simple because RocksDB's file requirements are simple, and also because we just implemented it in a very simple way. So there's only like a single on-disk structure. Basically, BlueFS is structured as a journal, a metadata journal, and that's it. There's no other sort of metadata structure. And so whenever there's a metadata operation, we just sort of append it to the journal. And when the journal gets really big, we just sort of rewrite the journal in a compact way so that all the file changes and deletions are squashed out. And so we just rewrite a new journal that, as if you had started from an empty file system and wrote exactly what's there. So it ends up being pretty simple. And all of the BlueFS metadata is in memory at all times. So when you look at the in-memory structure for, let's see, I think there's file, yeah, this is it. This is like the entire file system. There's a map of strings to directory references and a map of inode numbers to file references. And that's like, that's all of metadata, and it's always in RAM because when you start up, you read the whole journal, and that's all there. That makes it really simple. We don't have to have like allocation tables on disk or anything like that because we just sort of calculate it as we go. We load all the files in memory, and so we can look at all the files, what they've allocated, and in memory we can figure out what the free list is. So it makes the implementation very simple. And it works because RocksDB's files are always big, or almost always big, and so even if you have like a 10 terabyte SSD that's just full of RocksDB, it's going to be full of like 16 or 64 meg files, and so it's actually a few thousand or whatever. I don't know. It's not a large number, and so it's not a lot of memory, which means that we don't have to deal with paging or whatever. Keep it simple. So that's BlueFS in a nutshell. If you look in BlueStore and you look at like say mount, it starts with an underscore. It starts up by looking at making sure that it is actually BlueStore that it's trying to start up. Otherwise, it says you're trying to mount the file store with BlueStore. It's confused. Optionally, you'll do an FS check on startup. Open path will just open up some files in the varlib Ceph OSD directory just to make sure it'll like open them with an exclusive block so you don't mount the same thing twice. Verifies its FSID. Takes in a lock so you don't do it twice. Opens the block devices. So just instantiates those classes. And then the tricky bit is OpenDB, where it actually bootstraps BlueFS. So there's a create flag because the makeFS takes like a similar path here. So this code's slightly confusing, but we're going to ignore the create here for a moment. There's a file in the directory of in the varlib Ceph OSD directory that's called BlueFS. It says whether or not BlueFS is being used. In the case of BlueStore, in a real cluster, it's always being used. The only time it would just be false is if it's like a testing cluster for some reason. But yeah, so it says do BlueFS1, great. So if we are doing BlueFS, then it has all the special stuff it has to do. You know, it only works when the backend is RocksDB. We set up the block devices for the DB device and the wall device, because those are used by BlueFS. One of those is shared, so we keep track of which of those ones is the shared device. And then the funny bit here is right BlueFS mount. Somewhere in here, we actually create the blue rocks env. Where is that? Here's the RocksDB env. This is the RocksDB backend class. And so here, we actually instantiate it. So blue rocks env. This is our magic glue layer between RocksDB's backend interface and BlueFS. This other stuff is here for debugging. There's an implementation of that mirrors all operations to 2 backends. So when I was writing BlueFS, it would mirror it to BlueFS, and it would also mirror it to like the POSIX backend. And when you ever do any read operations, it would assert that the results are the same. So that's useful for debugging. This still gets triggered by some of the teleology tests to make sure there aren't issues. But right, it instantiates that env, and then it creates the actual key value DB, passing in the env to get it started. Okay, so we have BlueStore is basically still mostly a black box. It's sitting on top of a block device. We have RocksDB, which is sitting on top of BlueFS. So we have a key value database that we use for metadata. What else? Any questions about that so far before I keep going? I've been rambling here for 20 minutes. Okay, so let's talk about the allocator. There are 2 other sort of classes that are used here in BlueFS. One is the allocator, and one is the free list manager. And the distinction is that the allocator is the thing that's in memory that helps you decide what parts of the disk to use now. When you need to do an allocation, it says, what should I use? And it makes that decision. The free list manager is the part that manages how that's actually stored on disk. It's the persistent mirror of that, essentially. And they're independent. So the free list manager is an abstract class that's pretty simple. Basically, you allocate, you release things. They're tied to transactions because any allocation and release is persisted at a particular point when you make a change, and that's free list manager is responsible for managing that on disk state. The only other thing it has is enumerate, reset next, which is used when you boot up. When you first mount BlueStore, it goes and enumerates the free list and then gives it to the allocator so that the allocator is primed in memory so it knows what the free list is. So there's only one implementation of this that we actually use, and that's the bitmap free list manager.h, which is doing something slightly clever. Basically, it's dividing the entire device. It's a huge bitmap, and it's chopping that up into keys in the key value database. And so each key is, I don't remember. It's hard coded somewhere or other. Each key is, some number of bits, some number of bytes times 8, some number of bits. So each key represents some portion of the space. And if the key doesn't exist, then the space is assumed to be not allocated. And the reason why we do this is that when we update the free list, we're actually doing an XOR operation. We're using the merge operator in the key value database. The reason is that we want to have multiple threads that are making changes to what's allocated and deallocated, and we want them to work as independently as possible in BlueStore, which means that we don't want some central lock on what the free list is. And so if I'm allocating space that's next to two different threads, or allocating space that are like right next to each other, we don't want to have to coordinate between them updating that key and then submitting their transactions, most importantly, submitting their transactions in sequence so that you don't have a misordering that then allocates something that somebody was planning to write but actually hasn't committed yet. There's some ordering stuff with the way that those transactions are committed from two different threads, and we want to avoid all that. And so we use a merge operator, which means that the actual combination of two people allocating space next to each other is merged by the key value database at some point later in the future. This is sort of a feature of LSM databases. That's pretty convenient. It basically efficiently sort of collapses those overlapping nearby writes, merges them later. And so in this case, the free list implementation is sort of tied to RocksDB or LevelDB or some similar thing. And so, right, so this implementation is using merge operator. It's not super exciting. It all sort of boils down to this XOR function down here. So it turns out that allocations and releases are identical because they're just the merge operator is basically bitwise XOR, and so they're just flipping the bits from allocated to released or released to allocated. And so you'll notice that allocate and release actually both call XOR, which is sort of convenient and silly, but anyway, that's how that works. Allocator, on the other hand, is a little bit different. Allocator, its job is to load the whole free list into memory and decide what to allocate when. So the interface here is a little bit different. You pass too many arguments here. It's a little bit convoluted, but basically you want to say how much you want to allocate, in what size chunks, and optionally you pass it a hint that says do it sort of near this, so that we try to, like, if you're extending a file and you need to allocate more data, it'll try to allocate it sort of close to the other data for that file object. And then it returns a list of a vector of extents that are allocated. And then there's a release similarly. So there are a couple different implementations for allocator. The first one was called stupid allocator, which is reasonably stupid. It basically is a set of B trees in memory that bin all of your free extents into sizes, so small ones, medium, large, whatever, except they're all by powers of 2. And so when you allocate something, it'll say, I want things that are extents that are this big, it'll go to the right B tree and it'll try to get a chunk. And if it fails, it'll go take a piece of something bigger, or if it fails that, it'll add up a whole bunch of little things to do it. And that's the current default. There is a new one that is about to merge that Igor worked on that is bitmap based in memory, that is faster and more deterministic in the usage of memory, and for the most part more memory efficient. The problem with stupid allocator is that the amount of memory that it uses depends on how fragmented your free space is. So on an empty device, it uses like 0 memory, and on a very fragmented device, it'll use a lot of memory. You don't really know how much. And also it's not very fast because you're doing all this B tree stuff. The new one that Igor wrote is totally deterministic. You can just, it's like, I think it's like 30 megabytes per terabyte or something like that. It's fixed. It's exactly the same amount of memory at all times, and it's much faster. So as soon as that passes testing, we're going to switch to that because it is better. Right. So that's Allocator and the free list manager. Those are, I think those are the two other like main separate classes here. And then everything else is in BlueStore itself. So let's look at the types file. So BlueStore types in lowercase defines the low-level types that we're using for the on-disk format. So we can just walk through these since it sort of gives you an introduction to what the on-disk layout looks like. There's a block device label type. This is stored in the first 4K, the first block of every block device that BlueStore uses. And it includes things like the UUID of the OSD, so you can uniquely identify which OSD this device belongs to, how big the size is from BlueStore's perspective, how much of it BlueStore is actually using, the time that it was created, and a description The descriptions usually, I think it's like BlueStore Wall or BlueStore DB or BlueStore main, something like that. And then it has this just an arbitrary key value, a map of metadata about the device. This is a comparatively recent addition, but super useful. So it used to be way back when with file store, it was your device was an XFS file system, and we'd just sprinkle all sorts of random files in there. So if you go and you look in your varlib Ceph OSD directory, you'll see like who am I and a UID file. You see like 10 random little files of like 20 bytes with like random bits and pieces of stuff. Metadata about like how to start things up, like sort of stuff that you would sort of expect to see in like a super block in a file system. And in fact, in BlueStore.cc, you'll see we actually saw some of that, like in OpenDB. Oops. OpenDB, when we wanted to know whether we were BlueFS or not, or what the KV backend was, these methods here, read meta and write meta, are reading those little files. And so it's things like which key value database is the backend for my file system. Normally this is RocksDB with BlueStore, and this BlueFS is normally 1 for BlueStore, but it might not be. So these used to be just little files. With the block device label, the contents of that sort of metadata is also stored in this map, which means that when you provision a BlueStore raw device, you can use the entire raw device without any kernel file systems on it at all. All that metadata is stored in these label files. And then there's a tool called BlueStore tool that has a command called, I forget what it's called, prime OSDdir here, which basically takes all those meta things that are stored in that super block and it just writes them all out as files. And so now Ceph volume, when it goes to mount a BlueStore, it's going to mount varlib, Ceph OSD, whatever on a tempfs, in-memory RAM file system, whatever. And it's just going to write those like 10 little files out from the super block into that directory. And then it's going to start the Ceph OSD based on that. So all that sort of bootstrap stuff that the OSD needs to figure out that, oh, I'm BlueStore and I have BlueFS and all that stuff is there without actually having to create a literal kernel file system on the device. We put it all in the super block instead, in the block device label. Right, so that's that. But the key thing here is that it has a UID, so you always know which device is tied to BlueStore. A C node is tied to a collection. So the object store interface in Ceph has objects and collections. Collections are kind of like directories. In reality, they map basically one-to-one to placement groups. So each placement group has a collection. The only metadata about a collection that we actually have to store is how many bits of the hash is significant. So how much that PG or that pool has been split, basically. That's like the only metadata we need to know. So there's not much there. A long time ago, we used to have attributes on collections, but we don't anymore. There's an extent type, which is basically just an offset and a length. We are like slightly space efficient here with these so that when we encode them, well, first we only have 32 bits for all of our extent lengths in BlueStore. So object sizes cap out at 4 gigs and an extent similarly caps out at 4 gigs. In reality, you don't want Ceph objects to get more than like a few hundred megs. So this is not really a limit. We encode these types in BlueStore using varint for the most part. And there are a couple different variants. For LBA, if it's a logical block offset, the encoding makes assumptions that block offsets, the last 12 bits or whatever are usually 0 and yada, yada, yada. They do a bunch of stuff to try to pack them into fewer bits. Same thing with the extent length. Usually these are block aligned, and so there's just different variants for that. So it's a physical extent. There's this p extent vector, which you saw. It's just a vector of extents. There's some slightly efficient encoding, how we encode. If we're encoding a whole bunch of extents, we encode the first extent, and usually the other extents are nearby, and so we do, I think there's like a diff, whatever, we try to encode them efficiently, pack them in a bit better. Extent ref map, I think I'll skip. This is for reference counting extents that are referenced by multiple clones. So we know how many clones are referencing the same series of bytes. And so there's a special structure that basically is a map of regions on disk and how many times those regions are referenced. And so it sort of builds in the reference counting and the extent map into one structure. This blob use tracker, I'm going to skip this because it's a little bit confusing. And it's buried in there sort of the right after. Okay, the main piece is a blob. So this is the sort of the low-level representation of some region of disk that's being used by an object. So a blob is associated with some number of extents. So usually it's just one extent. One blob is one extent, but it might be multiple extents. And then there's a bunch of metadata about it because blobs might be compressed. They may or may not have a checksum associated with them. They might be shared by multiple clones, or they might not, which affects whether or not you can modify them, that sort of thing. So all that metadata gets encoded into the blob. So we've got this flag structure like these. We keep track of the length of the blob before and after it was compressed, if it is compressed. It may have different checksum algorithms that are applied to it. Usually we use CRC32, but maybe it's something else. And also the size of the block or the chunk we call it that you're checksumming might be different. So usually we have a separate checksum value for every 4K, but it might be that we're checksumming big chunks because we know that this object is only written once sequentially and it's also read sequentially, so we can store less metadata by having bigger checksums. And this is just a pointer to the buffer that has all the actual checksum data itself. So that's a blob. And it's got a whole bunch of little helper methods that do all kinds of stuff. You know, whether you can add a tail to it when you're appending to it, all kinds of things, all kinds of stuff. A shared blob comes up when you have multiple clones of the same object that are referencing the same blob. We need to keep track of some metadata about that sharing. So in BlueStore's case, when you clone an object, the new ONode, the new object, just has a copy of all of those blob T's. We just copy it and we basically flag them and say they're immutable, they can't be changed anymore. But then we have to keep track of how much of the actual data is being shared. And so that's what the shared blob is. And we use that ref map T I mentioned earlier, where we're reference counting extents to figure out how much of the actual data is still overlapping. And then the ONode. An ONode is the metadata for a single object. So it's analogous to an inode in a file system, but you know, it's an object. It has a unique identifier, which is like an inode number. That's globally unique across BlueStore locally. It's got a size, how many bytes. It's got attributes, sort of like extended attributes, just key value stuff. And then we have to keep track of the blobs that are used to comprise that object. The problem is that an object might have, you know, one blob, or it might have, you know, 1,000 blobs if it's like highly fragmented and there are lots of little things. And so we actually shard that map. That's called the extent map. We shard it up into pieces. And so an object may have one or more shards. And so the shard info is basically describing each of the shards, how big they are, what the offset, where they start, and what their size is of the logical object byte space from 0 to size. So from 0 to size, you're going to have some number of shards. And this is just describing how that's carved up. Let's see, there are flags associated, whether this object has OMap or not, whether it has PG meta OMap, I don't know, some other stuff, some helpers, encode decode. That's it for the ONode. The actual metadata about the blobs is stored in a different structure, so it's not part of ONode directly. I'll get to that in just a moment. When BlueStore is doing writes, what it usually will try to do is it'll decide what space, say you're doing an object write, it'll decide where the data is going to go. From the allocator will tell it, it'll allocate some bytes. It'll write the data to those bytes on disk. It will do a flush to make sure that data is durable. And then it'll commit the transaction in RocksDB that refers to those. That's what normally happens. But sometimes you're overwriting bytes in an existing blob, and so you have to do a read modify write cycle. Or sometimes it's just a small write and you don't want to do an IO and a flush and another transaction IO because it's less efficient. And so we do what's called a deferred op or deferred write. And this is where we basically, in RocksDB, we write that we're going to write to the location. It's a promise to do future IO essentially in RocksDB. So we have a single transaction that updates the metadata and promises to do IO later. And then once that commits, we actually do the IO. So that's what a deferred op is. There's only one type, is a write. These are the extents in the data that you can write to. So that's what that is. And you can bundle a bunch of these into a transaction. That's about it. And compression header, this is some compression thing. So that's a whirlwind tour of the on-disk structures. Let's look at the read path. I think that's probably going to be actually let's start with something simpler. Let's look at getAttr. This is going to be sort of the simplest thing. And we'll even start even before that. So if you want to read an attribute, you'll notice you have to have a collection handle, and you get a collection handle by calling open collection. So when in the OSD code, the OSD is actually opening a collection handle for every place and group that it has, and so it already has these handles all ready to go. If you look at open collection, it's calling get collection under the covers, which takes a read-write lock on BlueStore's map of collections, looks it up, and if so, it just passes a reference directly back to its collection ref. And those look like this. Let's say here. It's implementing the generic class and object store. It's got some back pointers back to BlueStore, pointer to which cache shard it's using. That C node that I mentioned at the beginning, which basically is telling you how dealing with it's how sharded this collection is. So we're passing a reference back to the OSD code or whatever directly to the structure, so we don't have any lookups and indirections later. And so for each collection, we're keeping track of the main thing here is all the O-nodes in this collection. Is this O-node map. O-node space is a fancy wrapper for basically a hash table. And here's like a lookup thing to look up an O-node by name out of that table, and some other stuff. So when we do our getAttr, somebody already has a handle of the collection. They pass it in. We typecast it back to our internal collection type. We take a read-write lock and we do get O-node to look it up. And if we don't get a hit, or we get a hit for an O-node, but it's marked as not existing, then we return enoint. Otherwise, we look up the attribute and return it. So this one's a pretty straightforward here implementation. There's quite a bit going on behind the scenes for this O-node map. Let's see if it's some fun in the header. Yeah. We have some sanity checks to just make sure that the object ID that you're looking up actually belongs to this placement group, this collection, based on the number of significant bits and the hash ID and the collection's hash bits. Just for debugging, we look it up. If we find that we don't have it in memory, if the in-memory structure, if we have it in memory, great, we just return it. If we don't have it, then we have to load it off of disk out of RocksDB. So here's where we actually start doing some I/O. So this is a string. All the stuff means that it's just stored in a mempool. So this is really just a string. This little helper function generates the right format for the key value, the key name in RocksDB. Given the OID, it stores into that key. and we do a store db get. So this db here is rocksdb get is actually just doing a lookup. If we get nothing, then it means that it doesn't exist, or that it's a new object. And so it depends on whether you passed a create flag, whether if you're doing a lookup to create it, or if you're doing a lookup and you want to fail if it doesn't exist. So if it's a new object, we just create a new onode. If it's not, then we also create a new onode. We say that it exists. We decode the value of that key, and we initialize the extent map. And this is where things get wonky, because BlueStore has sort of two modes of storing metadata about an onode. If there's relatively little metadata about the onode, it puts it all in one key value pair. So this we're getting an iterator to the key value here. So this decode part will decode the BlueStore onode T portion that we looked at. It's just the attributes basically and the sharding information. And then if there are no shards, meaning that it's a relatively compact object, there's not very much, then we're also going to all the actual extent map is stored in that same key. It's all sort of stuffed together because it's relatively compact. And so we'll decode part of the extent map for that inline portion. But if it's a big object, it's got lots of fragments and they're actually separated into separate key values, then we'll just initialize our information about what the shards would be, but we won't actually load them. And so that's what this init shards things does. And then later, when we actually are doing I/O to that region of the object, it may or may not have to load that shard in order to do it. So as an example of that, and then here it adds it to the onode map. So as an example, let's say we're doing a read. Here they're passing in a collection handle on an object and looks up the onode. The onode exists, so we make sure that we're sort of cropping it to the size, and then we call do read, which is the part that actually does the interesting work. So do read, you'll notice one of the very first things it does, it looks at the hints to decide whether we want to cache the read result or not for future IOs and so on. Crops the result. The first thing after that it does is this fault range function on the extent map, and that makes sure that the metadata about the allocation for this portion of the object is loaded into the cache. So it's faulting them into the extent map. And we can go look at that method, extent map. Here, let's look at what actually extent map is first. So extent map is a structure that maps offsets to blobs. So it's for one onode. The structure is for one particular onode. There's an extent map T, which isn't very helpful. Where is that defined? Extent map T. Oh, yeah, it's an intrusive map of extents. This extent map T. So let's look at extent really quick. Yeah, okay. An extent is one portion of the namespace. So within an object, there's a logical offset, which is like the byte offset within the object where it starts. Blob offset is okay. So it has a logical offset. It has a length within the logical object that it covers. There's a blob that actually stores the data for this extent, and blob offset is the offset within that blob. So you might have like a 64K blob, and maybe you have an extent that the first 12K of the file starting at logical offset 0 points to this blob, and the blob offset is 0. And then you have something else that was overwritten that includes part of the blob, and then after that, starting at 32K or something, you have another extent, logical offset 32K, for the second half of that logical length 32K, that points to the same blob with a blob offset of 32K. So it'll point to a portion of the same blob. probably help to have a picture of that, but you hopefully get the idea. Anyway, so that's basically just one extent. It's got some helpers here, but not too much. The main thing is that it is it's a boost intrusive class, which means that it's a member of a sorted set that sorts based on logical offset. Using the intrusive, whatever, boost intrusive code. So it basically sandwiches on a piece of the struct that has pointers for the red-black tree thing that boost intrusive is using. So that's extent map T is the actual set of those. So it's a sorted ordered set of extents, and extent map has that whole map in it. It also has these spanning blobs, which I'm going to ignore for now because they're sort of a oddity, not super exciting. I can cover that later if anybody wants to know. Remember, the overall extent map is sharded into pieces. So you'll remember in the O node we had to break. It had a bunch of sections of the object that basically describes which ones, how that overall object space is divided in different shards. Each of those shards is stored in a separate key value pair. This is a mirror of those same shards, which is just metadata about it. How many extents are in that shard? Is that shard loaded into memory? And are any of the extents in that shard dirty and need to be re-encoded when they get written to disk? And there's some stuff here for being a little bit more efficient about the which parts, how many of those extents are dirty for begin and end. But that's basically it. So when we call fault range, basically this looks up which shard for a particular offset for the start and the end, and it loops over these shards basically. So we get a pointer to the shard, and if it's not loaded, then we have to go load it here. So all this stuff will load that shard out of the key value database. So this generates the key name and calls dbget on it to load it into memory. And then we decode it into the extents, and we set loaded equals true. That's basically it. So then if you go back to do read, by the time we have finished this call, we have all the metadata about this portion of the object loaded into memory, and we can just sort of go ahead. So I think there's way too much code in BlueStore to go through in an hour. We've done this for an hour. Let me go through just the read code, the read path, and then we'll probably adjourn for now. Does that sound okay? Anybody still on? Yeah, we still have 27 people. Okay. So we have a region of the object that we're going to read. I haven't read this code in a while, so hopefully I can remember here. We're basically going to build a map of all the blobs that we have to read in order to satisfy that request. And so we're going to start at the initial offset in the extent map, and we're going to enumerate. We're going to walk the extent map. And for each one of those, we're going to figure out which blob it is, which sort of portion of that blob we want to read. We're going to build a map of the regions. Let's see, what is this doing? Buffer cache read. This is actually doing a read out of, this is trying to read it out of the buffer cache, the in-memory. So BC is buffer cache. So first we check to see if you have the result in memory. This may or may not succeed. So we look at the cache result. If we have it, great. If we already had it in memory in our buffer cache, great. If not, then we make a note in this blobs to read map that we need to read this blob from disk. And this is all tricky because all these blobs might be, we might only be looking at a portion of this extent, and the extent maps to a portion of a blob. And so there's lots of like goofy arithmetic here in order to enumerate this properly. But once we finish this loop, we basically know what it is that we need to read off of disk into this blob just to read. And so here we actually read it. So we enumerate, here's our IO context, which is going to keep track of our AIO, our asynchronous reads. and we're going to enumerate, we're going to walk over those blobs. So if the blob is compressed, then we have to be a little bit tricky because even if we only want a small portion of a blob, if it's compressed, we need to read the whole blob and decompress it as a whole in order to get that one little section of it. And so there's a slightly different path here. So in the compressed blob case, we're going to read the whole thing. We call this map function, which you pass to lambda 2, which says whatever it is that you do for this sub region of that blob. And in this case, we're going to call AIO read. This is a little bit goofy because we're actually, the read path is trying to be a little bit clever. If we're doing a read and there's only going to be like one, we're only reading one thing, then it's going to just read it synchronously. But if we're reading a lot of blobs, then it's going to do AIO. There's a little bit of overhead with the asynchronous IO because another thread has to wake up to do our completion. And so there's sort of a balance point, which is right here. So if there are more regions to read than during this blob, then we do AIO. Otherwise, we just do it synchronously. So anyway, we trigger, let's assume that this is a big complicated object. We're going to queue up the AIO for this region. We'll trigger the IO. It's going to go into this buffer list and the compressed blob results, which are sort of stashed here somewhere. If it's not compressed, then it's a little bit simpler. We just have to read the pieces. I guess it's not simpler, but it's different. We have to read the pieces of the blob. So we walk across the extents. And again, we are going to do AI read for all those sections. And they're going to go directly onto this result buffer list. And then if we did in fact trigger a bunch of AIOs, we submit them all to the block device and we wait for them to complete, make sure there wasn't an error. And then by the time we get to here, we basically read all the data and it's all sitting in a bunch of little buffer lists ready to be sort of assembled. So in the compressed case, if there was any of it compressed, then we have to compress blobs BL, then we have to go through and decompress it. And so we walk through again, we look for the compressed blobs. We first verify the checksum that the on-disk data was correct. Assuming that the checksum was okay, then we decompress it. And then we filter out the pieces, the actual decompressed pieces that we were looking for in the first place. And we also, this little bit here, if it's a buffered read, then we add it into our buffer cache. So we tell the buffer cache that I read this data and it'll make a copy in memory in case somebody comes along later. In the non-compressed case, it's a little bit simpler. We just verify the checksum. Also, we note that we read the data and we put the result in ready regions. So this ready regions map has accumulated all of our completed read pieces in the right spot, stored at the logical offset where they're going to go. And then finally, we basically send all of those pieces into the final read buffer, put it up by basically appending them all together. If there's a gap, then we have to put some zeros in between because sometimes there are holes in the object. If you punch a hole, we just don't point to anything. So we have to put zeros in the actual read result. And then we're done. We return the number of bytes in the buffer that we read. So that's the read path. There are a couple helpers that we used here. One of them was verify checksum. It calls a method on blob to actually do it. If there's an error, we go to some effort to try to figure out to tell the user what portion of the object it was that actually had the error. Decompress will pull out, there's a little header in the compressed data that indicates how it was compressed. And so we pull up the right decompressor reference here, pull up the compressor if we don't already have one, and then decompress the field. And that's it. That's the read path. Let's see. The write path is way more complicated. So I think, I don't know, do you think should I go through some of that now? Josh, what do you think? Should I keep this to an hour or just keep going? You there, Josh? I don't know. Anybody want to chime in? What do you think? We can also pick this up later. Well, let me give just a really quick high-level view here. So what did we look at? We looked at read. We looked at read. We looked at getattr. Pretty simple. There's all the OMap stuff. Oh, let me look at, we'll do the OMap stuff really quick because that's relatively simple. So all of the different types of metadata in BlueStore are stored in different regions of RocksDB. So most of it is stored sort of all together. All the object names mapping to their onodes and their shards are kind of stored in one big contiguous section. But OMap is stored separately, and the allocation bitmap is stored separately, and a couple other deferred IOs stored separately. So OMap, let's look at that. So if we do OMap read, what is it? Get OMap, what's it called again? OMap get. So let's say we're trying to read an OMap key value pair, whatever, from an object. Again, we're passing a collection handle and an object name. We'll look up the onode. If it doesn't exist, then we fail. If the onode doesn't have any OMap, then we can fail quick. There's this flush thing here, which is sort of an implementation artifact of BlueStore. Let's see. So this is a recent change. Well, maybe not this specific part, but there was a recent change in the mimic cycle around how the object store interface is implemented. It used to be with file store that everything was sort of asynchronous in that if you submitted a transaction, you wouldn't be able to read the transaction until you got the unreadable callback. And that was because file store was doing write-ahead journaling, and after it journaled it, it would go write it to the disk, and only then could you go read it. But this unreadable callback was like super gross. We had 2 callbacks for every transaction, when it was readable and when it was durable. And all the code in the OSD that had to read anything out of the OSD had to make sure that any changes it made before were readable before it tried to read them. It was horrible. And so in Mimic, we basically got rid of that callback completely, add some hackery to file store to make it appear as though things were immediately visible, or to block if they weren't. And in BlueStore, it's mostly things just worked out because when you queue a transaction, when you queue a write, it synchronously updates all of its in-memory state, anything that's cached. All of the things that are dirty and not yet committed yet are always in the cache, and so you could read them, and you could see the sort of the leading edge state of the system, even if it hadn't been committed yet. And so for the most part, the BlueStore implementation worked out just fine. The only part of it that didn't is, there are 2 things. One is OMap, because BlueStore doesn't actually cache OMap data. It just defers that, it just passes it straight through to RocksDB. And if you queue a transaction, but that transaction hasn't actually been submitted to RocksDB yet, and then you go and try to read it, then it won't see the thing that you haven't queued for RocksDB. It wouldn't see the latest write. And so that's what this flush here is. This basically just blocks until any previous transactions on this object have actually been submitted to RocksDB. Because immediately after that, we go and we actually try to read out of RocksDB in order to get we figure out what the key, the starting and ending keys are, and we go and we enumerate and whatever. We get those keys. Sorry, I only got a few more minutes. Right, so that's the one place where this crops up. The other place where it comes up is when listing objects in list collections, not list collection, but collection list, which is enumerating objects in a collection. There also we're just walking through RocksDB's key value data. And so also we have to do a flush somewhere in here to find where it is in order to make sure that that state is actually on disk. But all of those, here it is right here, here's the flush. All that has been pushed into the object store implementations now as of Mimic. And so the OSD code has been simplified. It doesn't have to think about those issues anymore, which is a win. But collection list here is basically figuring out what the key is for your start and end points that you're listing. And it just goes and gets an iterator for RocksDB, and it parses the keys and wraps them up. It's a little bit confusing because of this temp object thing, which is sort of sort of a separate mirror namespace where for each collection you can have temporary objects that are associated with the collection but don't sort in the same way that the other objects do, and they get cleaned up when you restart the OSD. So there's a bit of annoying stuff around the temporary objects. But aside from that, the main part of the loop is pretty simple. It says, is this an extent shard? It's either an extent shard or it's an O node. And so if it's an extent shard, you skip it. And if it's an O node, then you parse it into an OID and you put it in the result, you continue. So this is sort of the crux of the list objects loop right there. And I think that's probably enough for today. Maybe we should do another one of these where we actually dive into the write path, which is at least as complicated as everything we've talked about already. Because that'll take another, chunk of time to get through. Okay. Any questions on everything so far? All right, so these are going to be, this is all recorded, so this is all going to get posted on YouTube, and we'll do a follow-up one in whatever the next time slot is. Thanks, everyone. See ya.